So in this module, we are going to see small size simulation examples where we can implement through spreadsheet applications. And the most known spreadsheet application is, of course, Microsoft Excel. So we are going to practice our applications also in Microsoft Excel as well. So this video is just going to be a introduction on these applications, and we are going to expand the size and the complexity of our applications in the following weeks in Spreadsheet Simulation. Okay, so let's move forward and let's give the outline. First, we are going to understand the concept of simulating randomness. And what is randomness? Actually, you know this term, the concept random, from the probability course, right? So we say that an experiment is a random experiment. It shows an inherent variation in the outcomes, right? So if the outcomes of an experiment are not predictable in advance, and if it shows some variation, then we say that this experiment is a random experiment. And randomness is a phenomenon which is observed in real life very frequently. Therefore, if you are going to create a simulation model for a real life system, then you definitely need to consider the fact that there is randomness in the components of this system. And then we are going to talk about the random numbers. And that is just going to be a passage through the next chapter, because the next chapter is actually related with random number generation. So this is just going to be a passage through the next chapter, next module of this course. So let's define the spreadsheet simulation. What is a spreadsheet simulation? A spreadsheet simulation is a simulation that is carried out on a spreadsheet, on a table, and using applications such as Microsoft Excel. And which type of simulation examples we can carry out in spreadsheet simulation? The relatively simple ones, actually. If you are going to create a simulation model for an assembly line or a complex manufacturing system, in that case, spreadsheet simulation is going to be not enough to manually handle this type of simulation models. So you definitely need a software or a programming language to create the simulation model of this kind of complex systems. However, for example, for simple queue structures, which we are going to learn in the following weeks as well, we are going to learn about the queuing simulation. For queue applications or for Monte Carlo simulation, spreadsheet simulation can be a good tool to use. And our aim here is not to learn how to formulate or develop the spreadsheet simulation models. Actually, we would like to introduce and illustrate some of the key concepts in this spreadsheet simulation. So actually, our intention is to create complex simulation models, not for simple systems, but we need to start from simple at this point to understand the main concepts of the simulation. And as it says, the spreadsheet has severe limitations for most complex real-world dynamic event-based simulations. So what we need to create a simulation model for such systems is a simulation package or simulation software package, or a general purpose programming language. Either it can be a high level programming language, you can use Java, MATLAB, R, Python, or you can try to use a more complex one like C or C++, but the best way to approach this problem is to use a software package. There are many software packages, as we have mentioned, such as Arena, Simulate, and ProModel. There are many software packages to implement complex simulation models. The best is to use such software packages in order to create a complex simulation model. So what we know about the real life is, as we have introduced in the beginning, in real life systems, what we see is at least a few of the components should be modeled randomly. So we need to consider them as random, because if you want to create a deterministic arrival process, then you need to consider everything that influences the arrival behavior of the customers. But you do not know it, because arrival process is an exogenous event which occurs outside the system. And you cannot fully put everything in the model which happens outside the system. And therefore, what we are going to do is we are going to assume that the arrival times are random and they are following a certain probability distribution. Okay, so most of the discrete event simulation models here contain one or more random variables as inputs. So if you imagine a banking system, the inter-arrival times of the clients to the bank, or the service times when they are trying to withdraw money or deposit money, these service times are also random as well. And there are certain distributions that you already know from the probability course, which can be helpful to model such distributions. I mean, for example, the most common distribution, probability distribution that can be used to model the inter-arrival times is the exponential distribution. And we can use normal distribution or gamma distribution to model the service times. For example, for a restaurant system, the released orders by the customers or customer groups are also random. Okay, not everybody orders the same food or same drink. So we need to use a distribution again to model if they are going to order a certain type of food or drink. And Bernoulli distribution here can be a good candidate to model because either you order the food or you do not order the food. So it is either 1 or 0, and it basically follows the Bernoulli distribution in this case. And in a warehouse system, there are different packages coming to warehouse to be stored, and these packages have different attributes, right? The size of these packages can be different. If you consider the packages as entities, one of the attributes that they have is the size of the packages, and it's an important attribute for the warehousing problem because we are going to test the capacity constraint depending on the size of the packages, right? So these attributes, the size of these packages, are again random. So they should be modeled randomly. Now, how do we get random quantities for spreadsheet simulation? So if you are going to generate an artificial history of the original system by creating a simulation model, then all of these random variables or random inputs should also be generated as well. So if we are going to, for example, create a scenario for one day for the banking system, then we need to create an artificial arrival process that happens or that occurs on that day, specifically for the clients, right? So in order to generate this artificial scenario, we need to generate inter-arrival times, but these inter-arrival times should also follow the same probability distribution as the original inter-arrival times that we observe in the original system. So the question here is this: how can we generate random quantities that follows a specific probability distribution? Now, this question is not very easy to answer at this point, but we are going to answer in the following weeks. So at this point, what we are going to do is we are going to start from the simple and to learn how to generate randomness, which follows uniform distribution between 0 and 1. So you know the continuous uniform distribution, right? Continuous uniform distribution is defined within an interval of real numbers, okay? And we have a standard uniform distribution, which is specifically distributed between 0 and 1. And the random variables that follow standard uniform distribution can take any real value between 0 and 1 with equally likely chances, right? So our objective here is this: how can we generate randomness which is uniformly distributed between 0 and 1? If we can do that, and then it may be possible for us to convert this randomness to other probability distributions as well. I mean, if we can generate randomness which is standard and uniformly distributed between 0 and 1, then we can convert this randomness to other probability distributions. So what we are going to call these random quantities which are uniformly distributed between 0 and 1, we are going to call them random numbers. What is a random number? It is a randomly generated quantity in the unit interval 0 and 1. So it is supposed to take any real value between 0 and 1. However, please do not forget this, my friends. If you are going to use a computer software to generate this random quantity, random value between 0 and 1, what computers can generate is only rational numbers. If you want to determine the square root of 2, it has infinitely many digits after the decimal point, and you can approximately determine that number, but no computer can exactly calculate that value. So square root of 2 or pi, number pi, these are just theoretical values, okay? We are using approximation for those. So even if we want to generate a random number that is supposed to be distributed in a real value between 0 and 1, what we can practically generate a rational number. But it's okay. I mean, it doesn't matter. I mean, we wouldn't understand the difference in any way between a rational number and a real number when it comes to the number of digits that the computers can generate, right? So after the decimal point, ordinary computers can generate up to 15 digits after the decimal point, and this is just enough for us. Now, generating other type of randomnesses other than the standard uniform distribution, it begins with generating a random number, it says. So let's just focus in the beginning if we can generate a standard uniform random variable in quantity, and that is what we call a random number. So of course, we are not just going to generate this random number for once, we are going to generate a sequence of random numbers for replication purposes. So if we are going to generate a sequence of random numbers, are we going to do it by using an algorithm? Actually, yes, we are going to do it with an algorithm, but what we expect from this sequence is two properties, and these two properties are too important. First of all, if you intend to draw a histogram of these random numbers value generated in a sequence, the histogram should imitate the probability density function of the uniform distribution. So you know uniform distribution has a constant probability density function. So the sequence must have a histogram with frequencies which are approximately close to each other. So basically, if you divide the unit interval, 0 and 1 interval, into many equally distant subintervals, the number of random numbers that we observe in each interval, in each subinterval, should be approximately close to each other. So therefore, we can say that they are uniformly distributed. And the second thing, they should be statistically independent from each other. So when you are going to generate a new random number between 0 and 1, you should not be influenced by all random numbers that you have generated previously, okay? Now, these two properties are too important, and unfortunately, human mind is not very capable of applying these two rules. So what we need is an algorithm, and what we need is a computer to perform that algorithm to generate a random number sequence which conforms to these two properties. Now, before learning how to do that, first let us learn that there is basic commands in Microsoft Excel actually performing generation of random numbers. So the command rand, so you write an equal sign rand and a parenthesis without writing anything inside the parenthesis. This command generates a random number between 0 and 1 with an acceptable number of decimal digits. So after the decimal point, after 0, after the decimal point, we have a quite reasonable number of digits that we can observe if we use this command, and therefore this is a very successful command to generate random numbers in Microsoft Excel. Now, at this point, it is possible for us to talk about another type of randomness, again, which can be imitated by a command line in Excel. It's the rand between function, and it is using two arguments with a semicolon separating them. And it is basically generating a random integer value between x and y with equal probability. So, for example, if you write x to be equal to 5 and y to be equal to 10, how many integers do we have from 5 to 10? 5, 6, 7, 8, 9, 10. There are 6 integers here, and this command is generating one of these 6 integers randomly and independently each time with equal probabilities every time any value has 1/6 chance, okay? Now, it says both of these functions generate quantities. The first one generates random rational numbers between 0 and 1. And the second one is generating random integers between two integer values. And they can generate these quantities independent of the previously generated quantities. However, there is a question mark here. So I am claiming that they are independent, but actually they are not, because they are generated by an algorithm. And if you are using a known algorithm to generate random values, how can they be random? So the question is very simple, right? So actually they are not independent, but they seem to be statistically independent, and that is just enough for us. So as you can see, the second property here, the subsequent numbers generated should be statistically independent of all previous numbers generated. So statistical independence is just enough for us to use the randomness and as assuming that they are independent.